So in our last lecture, we saw a couple of downsides with hash indexes. We have to keep hash indexes, overall hash indexes in memory, and the range queries were not that good. And with writing a lot of stuff, it didn't scale that well. So this is where our SS tables and LSM trees come into picture. Limitations we saw with log file segments plus hash indexes are easily fulfilled by SS tables and LSM trees. SS tables full form is sorted string table. So you can see in the name itself, it suggests sorted. So definitely there would be something related to sorting, which will optimize a lot of things for us. And then the full form of LSM trees is log structured merge tree. But across this video, I'll use it, the short names as SS tables and LSM trees. One big advantage is we have sorted keys in our log file segments. So earlier we saw with hash indexes, there was no concept of having sorted keys. Here we have sorted keys within our log file segments, which we will just see down below. So compaction plus merging, which we saw with hash indexes, that was quite straightforward. That is explained a lot more in depth. Check out that video if you haven't yet to understand more in depth how SS tables and LSM trees solve all the problems that we faced with hash indexes. Here compaction and merging, it is something similar to merge sort. So merge sort is done, which produces a new log file segment. Again, all keys would stay sorted as we have done merge sort. Okay. So let's see, these are our segments from the diagram. Segment 1, we have segment 2, segment 3, and then this is the merged result. Let's try to understand what is happening behind the scenes. So these segments, they are, compaction is done over there. As we discussed a bit in depth in the earlier video of hash indexes, compaction, it would keep the recent value of those keys to have within that segment unique key value pairs and would drop the keys, the same keys with the older values. So if you see in this segment, you can see all keys, handbag, handful, handicap, handkerchief, handlebars, hand printed are unique with values, and these values are the recent most values on these keys that have occurred. If there would have been, let's say, handbag in within the same segment with a value of 8750, okay, so it would have kept during compaction as handbag with value 8786 and dropped the older value of 8750. Similarly, compaction would have played out with segment 2, compaction would have played out with segment 3. So you can see here a new log file segment has been created. Compaction and merging plays out together, and you can see the new log file segment which is created all have unique keys in it. So if you check, what would have happened is it would have gone and checked for handbag. Here it is handcuff. Here it is handful. So it would have picked handbag with 8786. Then the cursor would have moved to handful, handcuffs, and again handful. Now merging is also being played out. Try to visualize it similar to a merge sort. So if you see, you have handful and you have handcuff, right? So you can see C comes before F. So C is less than F over here. Rest all these characters are similar. So first handcuff would come up, and then handcuff is just present in this as these three segments are getting compacted and merged. So we will get handcuff with 2729. Then the next pointer would come to handful. Then you have handful over here, then handful over here. Now you have three handful, keys same. So compaction would play out and it will pick the most recent value of it. So it will pick up 44662, which has been picked up here if you see. And similarly, it would keep on progressing further and compaction and merging would keep on playing out to form this, eventually this new log file segment. Once this new log file segment is formed to save out memory, it will drop all these older log file segments from which the newer log file segment has been created after doing compaction and merging. Advantage of this sorted log file segment are that we don't need hash index for all the keys to be in memory. So if you see with hash indexes, we needed all the keys to be in memory. But as we check, we can see over here merge sort played out. So all the keys that eventually got formed in our log file segment are also sorted based on their keys. So we can play out this advantage by not keeping all the keys in memory, and instead of that keeping couple of keys in memory only. So we keep some of the keys in memory only, and this is termed as keeping a sparse index. So one key for every few kilobytes in our log file segment. So what we do is we pick up a key and keep it in our sparse index from our log file segment, and then after few kbs we again pick a key and put it in our sparse index and pick that key from the log file segment, and so on. So you can see you have couple of log file segments. If you see here, you have the sparse index in memory which will be created won't be of all the keys that is present in these segment files, SS table on sorted segment files, SS table on disk. So the sparse index won't have all the keys present. As we just discussed above, it picks one key for every few kilobytes in our log file segment. So let's say it picked handbag at 102134, and it picked after that, after a few kilobytes, it picked handsome of 86478 with that value. So what sparse index does is it keeps a byte offset for them. Okay, so let's say it kept handbag with a byte offset and then handsome. So if you can get handbag from the sparse index, you can get handsome from the sparse index, and if you got a key which has handbag previously and handsome after that, so you can reach to that key as things are sorted over here, unlike which we saw in the hash indexes. Over here things are sorted, so you can then do a linear search between handbag and handsome to reach to that. What I mean by this is how key lookup is done. Example, my key is handoff. Okay, so in the sparse index we will do the lookup, and I want to do the lookup of handoff. So you can see we don't have the exact key handoff within our sparse index. We know keys are sorted, right, in our log file segments. So I got handbag, let's say I got handbag from the sparse index, and then I got handsome from the sparse index. So I got the byte offset of the handbag. As we just discussed, the sparse index keeps the key alongside the byte offset of that key in the log file segment which is present. And then I got the byte offset of handsome. Then what I can do is we can make a linear searching among keys within that few kilobytes. As I just discussed above, that sparse index is made that every key is present after few kbs in the log file segment. So we can then eventually make a linear search from handbag to handsome, searching till we got handoff, and then I can check the byte offset, and then I can extract out the actual value of the handoff from the log file segment. So we make a linear searching among these keys as we created sparse index based on those keys under every few kbs blocks, right? As you can easily see from the diagram, which is now self-explanatory, that you have handbag and handsome, and then you would linearly traverse from this handbag to handsome until you got handoff, and you can then extract the value, and you got the handoff with the value at 5741, right? So basically you didn't have to traverse linearly through all the keys to eventually reach to handoff, similar to what we looked up into our hash indexes. Now important question comes up. Okay, we had the keys as sorted in our log file segments. From that we were easily able to create our sparse index, which consisted of key alongside its byte offset after every few kb blocks. But how we got all these keys in our log file segments has sorted in the first place, right? So we assumed that we got the keys and compaction and merging were being played out and so on, but the keys that we got into our log file segments were all sorted. So how we reached to that in the first place, that's an important thing to know. So we use balanced binary search tree based on keys. Why balanced and not just binary search tree? As with a binary search tree, you know that if a skewed binary search tree comes up, its height would go to big O of n in the worst case. For example, if you got 1, 2, 3, 4, 5 value nodes, that would become a skewed binary search tree. And if you want to traverse to 5, then you have to go from the root node, which is 1 to 2, 3, 4, and 5, due to its skewness. That is why we use here a balanced binary search tree. As with the balanced BST, the height of tree still stays big O of log n. With balancing, it takes the height of the left subtree and the height of the right subtree, and the difference of that is always less than equal to 1. This is how balancing plays out, maintaining at every moment, at every subtree, height of the left subtree and height of the right subtree, the difference of that stays less than equal to 1. For example, you have a tree, balanced binary search tree, how it would play out with if you want to plug in a new key, donuts. So let's say you have a key as fries with some value, then you have burger, then you have apple, then you have pizza. Now, if donut comes up, how you would do that is, so you have D for donuts. So you have fries. So D is smaller than fries, so it would go towards the left side. Then you have burger. So B, it would compare donut with that. And then donuts is bigger than burger, so it would come on the right side of it. And it has an empty space, so donut would be plugged in over here. Now, if you check the difference in the height of the left subtree and right subtree, it needs to be 1 to keep things balanced. So if you see at the level of fries, if you see the height of the left subtree, that is 2, height of the right subtree, that's 1. So 2 minus 1 is still less than equal to 1. For burger, height of the left subtree is 1, height of the right subtree is 1. So 1 minus 1 is less than equal to 1. So it's balanced. Now this balanced binary search tree with all the keys in it and the value, this is kept in memory. Now, but still you might think how we would get the sorted keys and their values. For a binary search tree, as we know, the in order traversal over its keys give us the sorted keys. So for in order traversal, for a binary search tree, which is left, root, right, we get the keys in a sorted fashion. So if you check, so you will get for in order traversal, it is left, root, right. So if you check over here, so you go first towards the left, then you go towards the left. So you will get apple, then it is root. So you'll get burger, then you will check the right. So you will get donuts. And then this left subtree is covered. Then you check for fries, which is the root. And then you move towards the right. And then you get pizza. So apple, burger, donuts, fries, and pizza. This is what we get after doing in order traversal on a binary search tree. And we have balanced binary search tree with us over here. So if we observe, we just mentioned keys are sorted over here. Then this goes or flush into our SS table after a certain threshold is reached on our mem table. So this balanced binary search tree, which is kept in memory, is also called as mem table, and the log file segments which we were calling out above, those are called as SS table. So this mem table, what happens is we define a certain threshold, like this mem table would be filled up to a certain threshold, and after that this gets flushed into the SS table. Let's see how this is done through a diagram. So some data comes up. So write data with a key and a value. What happens is it goes into the mem table, gets filled up in the balanced binary search tree. It gets plugged into that, the tree is balanced then, and this all is in memory. And after a certain threshold of mem table getting reached to a certain threshold, it gets flushed into the SS table, where we also checked, we also have a sparse index created out of that SS table, which is picking up couple of keys after certain few KBs blocks. And then from the mem table, during the flushing, you can extract out the sorted keys and then their values by doing the in-order traversal on that balanced binary search tree. And in this way, by doing the in-order traversal on your mem table, which has the keys and that value in and their respective values in a balanced binary search tree plugged into the SS table in a sorted way based on keys. So this is how writing of data would be done. Now the writing is now write data comes at mem table. So it could be the case that we might lose the data what's there in the mem table before it gets flushed to the SS table. There could be a case. So what we do is to increase the durability, as soon as the key plus a value comes up, while writing it to our mem table in our balanced binary search tree, we also make an entry to a commit log to increase the durability, so that if we lose the data in the mem table, so that can be recovered from the commit log. What happens with the case of reading of data? LSM system is good with keys that exist, but can slow down when keys don't exist. What we mean by this is, for keys that don't exist, let's say we have a key which doesn't exist in our mem table and also earlier in all the data that got flushed from mem table to our SS table. So if a key that doesn't exist, we first check it in our mem table if it's present there or not. If it is present, then we return from there. But this is the scenario where key doesn't exist. Then we need to check in for that key in all our SS tables, from the most recent SS table to the oldest SS table, to just eventually conclude that key doesn't exist, right? So this flushing was happening from mem table to SS table, and SS table also have some certain threshold. After that is reached, a new SS table is created, a new version of that, and then the new keys that are being written to the mem table gets then flushed down to this new version of this SS table, and so on. That keeps on going. But if the key doesn't exist, then we check it in our mem table, and then we have to check in for that key in all our SS tables, and eventually to conclude key isn't there, there need to be some good case, some optimization for this edge case that key doesn't exist during lookup. So this is where Bloom filters bring into some optimization over here during lookups. A Bloom filter tells us about if a certain SS table has the key. By has, it means might. If the Bloom filter says that these certain SS tables has the key, by that the Bloom filter means it might have the key or might not, or it doesn't have the key, and there is surety in that it doesn't have the key. So in short, SS table doesn't have the key in it. There is surety in concluding that an SS table doesn't have a key, what we are looking for, or an SS table might have the key. There could be a possibility that eventually doing lookup within the SS table might have the key or might not. Say key isn't there in mem table. Okay, so we have, say, now 10 SS tables which have been created. So from version 1 to version 10, 1 being the oldest, 10 being the recent one, for example. We have to sequentially look into all of them. Even though lookups inside an SS table is better than our earlier hash index because of the sparse index being present and keys being sorted. Now, if we don't use the Bloom filter to get that optimization, what would have happened at the time of lookup of a certain key, that we checked into mem table, we didn't get the key. Now that mem table was balanced binary search tree. So the lookup for mem table will go to big O of log n, which is the height of a balanced binary search tree. Then let's say 10 SS tables till now are created. So we will look up in each of these SS tables, even though we have some optimizations already with SS tables, with the keys being sorted and having sparse indexes created out of those SS tables. Still, if you see, lookup is quite a heavy computation thing. And the worst case would be that the key wasn't even there. With Bloom filter, what it does is, say it says on 8 SS tables that it doesn't have the key. So as we looked above, that it concludes it doesn't have the key with surety. So 8 SS table lookups are now out of this picture. And on 2 SS tables, it said that it might have the key. So with might, we still have to go and do the lookup. Then we do lookup on these only 2 SS tables, eventually finding the key or not finding the key. But still, it brought down from 10 SS tables, for example, just supposing from 10 SS table to 2 SS tables, eventually saying that the key isn't there.